runs into a segment, creates 90 degrees, and it, like you said, it's like a midpoint. Okay? So a perpendicular bisector does two things. It bisects a segment, and it creates two right angles. For example, if I say that I have a perpendicular bisector CD, and it's the perpendicular bisector of AB, we know two things that we can do. First thing you can do, obviously, is draw the two right angles. Obviously, it's perpendicular. So you can draw your two right angles in. Super easy. And then we know that the segments then are created, they're equal. So you get that right away. Now, when you look at that, it doesn't have anything else. It's just basically two segments. Now, what happens if I draw in CA and CB? What do you create? Create a triangle. So if I draw in CA and CB, what can you say about segment CD? Yes, sir? Reflexive, very good. You could say that it's reflexive, couldn't you? Which therefore means that you get two triangles that are congruent to each other. How do you say that those two triangles are congruent? Because of what? Side angle side, very good. Okay, everybody see that? Now, what happens here is that you get this thing of side angle side, which means then, what can I say about CA and CB? They're also congruent. Because remember the whole corresponding parts theory, that whole CP-CTC thing. So what happens here is that whenever you get a perpendicular bisector, whenever you have a perpendicular bisector of a segment, you can automatically create two triangles that are congruent to each other because of side angle side. Because it does not matter where you are on that perpendicular bisector. It doesn't matter where you are, because no matter what, won't this segment always be reflexive to itself? It doesn't matter. So as long as you are on a perpendicular bisector, you always create, well, actually create an isosceles triangle. So that's kind of the thing we have here. If you are on a perpendicular bisector, and it's kind of tough to do this one without a lot of words, so I apologize for that. So if you are on a perpendicular bisector, you're always equidistant to the endpoints of the segment. I'm trying to think of an easier way to say that. If you're on a perpendicular bisector, you're always equidistant to the endpoints. So if you think of it as, it creates the legs of a what do you call it? Isosceles triangle. So if you're on a perpendicular bisector, you are always equidistant to the endpoints of the segment. Okay. And I apologize that it's kind of wordy. Yes, ma'am. Equidistant just means equal distance. Equal distance. So again, what you wind up with here is that no matter what, the perpendicular bisector always creates basically a side angle side reference between two triangles. No matter what. Because you will always have a reflexive side. You will always have congruent right angles. And you will always have segments that bisect. You'll get the two congruent parts, you'll get the right angle, and it'll reflex. Now, don't worry, we're not going to do proofs with this, but we will want to so we can say this a couple ways. If you're on the perpendicular bisect, you can always do this in the segment. Or if you're equidistant to the endpoints of the segment, you are on exactly. You can say it forward and backwards. Okay? It's one of those what we call a biconditional statement. It's true going either direction. Okay? Back to me later. Think about it. Okay? So, it allows you to do stuff like this. And again, it's not going to be horrible, crazy, difficult math, but it's going to be, as we get into this, we're going to get into bigger picture, more stuff going on at once, where it takes a couple extra minutes to see what's going on. So for this example, you're given triangle ABC, and you have a right angle down where BB is 80. If you have one right angle, what is the angle on the other side? Okay, it also has to be right angle. Okay. What is the segment AC bisect in this case? Okay, and we know that because it's got tick marks. If that's the case, then do you have two congruent triangles? Yeah, we have the two triangle sides, two congruent sides because of sine equals side, because you can say that BB is reflexive without having to do a lot of work. Remember when we talked about reflexive property? That was one of the ones that you can always just automatically say without having to show much work through it. So I could just mark my diagram knowing that this has to happen, which creates the two triangles being congruent, which means the segments on the outside have to be the same. So algebraically, you set them equal to each other. Now, this is one of those where normally I would say pick on the little guy, and I would subtract the 4x, and then I'd have to add the 10. Sometimes people tend to freak out when they have a 0 on one side if they do that. So I'm just going to move the 6x. But remember, when you move the 6x, you're subtracting it. So you're going to get a, what's 4 minus 6? Yeah, just got to remember you get a negative here, okay? So you get the negative 2x is negative 10. Because remember, the 10 has the minus sign in front of it. What's negative 10 divided by negative 2? 5. Which means, if I substitute back in, they should both be equal. So what's 5 times 4? 20. What's 6 times 5? Subtract 10 and you get 4. Which means you didn't done goof. I know. You can math correctly today. Maybe not tomorrow, but maybe just today. Okay? Not terrible, right? Wait. I'm sorry, what's that? Yes, yes, yes. What I did here is I'm just taking this value of x, I'm substituting in. So I get 4 times 5, and that got me 20. And then I do 6 times 5, subtract 10, and that also equals 20. I was just doing the quick substitution for that. Okay. Oh, I always forget. You always like me to write that for you. I always say it, and I always forget. You want to see it written down. I'll do that next time. Okay? Not so bad? Well, honestly, today it doesn't get too crazy. I got like one example that's awful, but other than that, it's not bad. Try again. Take a second to try it. couple months since we've done a lot of algebra, we're mainly working so much with groups lately. Make sure you start bringing your calculators to class a lot more regularly. So you need to make sure you understand how to use them correctly. So, is QS perpendicular to PR? Has PR been bisected? So therefore, that you know that PQ has to equal RQ. So you map it. Are we at the point now where we can do both steps at the same time and not be too terrible at it? What I mean by that is I'm going to subtract 3n, add 7, do all of it at once. Okay? You get 3, and then what you do to make sure you did it right is you take that value of 3, you substitute back here, you get 3 times 3, subtract 1, and you get 8. If we do the same thing here, 5 times 3, subtract 7, and you get 8. And like I said earlier, it's not that you have to check it. It's a really good idea that you do check it because you can so easily make a dumb mistake and not realize that you did it. Okay? What's that? Oh. Sorry, we're going a lot slower. Sorry to ruin your day. Okay. All right. What does an angle bisector do? Bisects an angle. Obvious. Now, excuse me. Again, we've looked at this. Oh, before I get to angle bisector, real quick. With mid segments, how many of them did we have in a triangle? Ladies and gentlemen. How many mid segments were in a triangle? 3 of them. How many perpendicular bisectors do you think are in a triangle? 3. And there's going to be a whole lot of stuff that happens with them. There's a lot of stuff that's going to happen. Obviously, I didn't draw the other part of the bisector itself going through, because sometimes they don't always line up into the vertices. Okay? But they get like that. Angle bisector. What does an angle bisector do again? When you bisect an angle, what's created? 2 congruent angles. Good. So if I take an angle and I cut it in half, that's not even remotely close. That's better. When I take an angle and I cut it in half, you get 2 congruent angles. And we would just mark that in our diagram with just the little quick tick marks, right? Okay. Now comes the idea of how do you measure something? Now, right now, so if I wanted to measure something, yeah, it's one of those wanted to measure the height of my water bottle. If I wanted to measure the height of my water bottle, do I measure it vertically or do I measure it diagonally? Vertically. Now, when you measure something, do you guys remember the closest distance between 2 points is always a straight line, right? Okay. So when you measure with the straight line, even if I'm measuring to the wall, if I go this way, it's still a straight line, isn't it? All lines are straight. But more specifically, if I'm going to measure from here to the wall, the shortest distance would be when I'm perpendicular to the wall. Okay? Because if you're going to walk straight at it, you'll run into it at a right angle. If I run over to this way, it's going to take me longer to get there. Does that make sense? So what we're looking at here is if you pick any point on an angle bisector, you pick any point on an angle bisector, from that point to the sides should always be perpendicular. And what happens is that distance will always be the same. Okay? That distance will always be the same. And if you look at it, you wind up with dun, 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 angle, angle, side. Okay. Not only does it have to show you this right away, because even if I do this to start with, oops, it's out of the way. Before I even tell you about the being equidistant to the side, if I just draw a right angle to the side, that right angle and the other right angle has to be congruent, doesn't it? Because all right angles are congruent?
Yeah.
Same idea goes for when you're a point on that. This distance is always itself, isn't it?
Yeah.
So that would just also be reflexive, wouldn't it? So if I do that, you get angle, angle, side. It works the same. Actually, move this right angle on the inside here for you to see it better. You get angle, angle, side when you're dealing with angle bisectors, which therefore means that if you're on the angle bisector, you're always going to be equidistant and perpendicular to the side. That's another wordy thing. If on the angle bisector, if you're on the angle bisector, you're always thanks, jerk. Perpendicular and equidistant to the sides. And again, this works itself out to being just a lot of really quick algebra problems. It's not going to be horrible, scary, that you have to do a lot of proofs or anything like this. But if you start to think about the proof of doing this is really easy because we just did. Angles are bisected. You're always going to be perpendicular to a side. Gives you another angle. And if you're on that bisector, you're always going to be reflexive going to that vertex. So that length never changes. You will always, always, always have angle, angle, side. That just, what's that? Thank you. We should have spares in case you guys want to buy one. They're $10. I'm not going to wear it every day for the rest of the year. I smell it. Okay. So again, like I said, we'll be able to do stuff like this. Yeah, even more so. I knew they were coming today. Had I known they would have been here early as they showed up today, I would have wore short sleeves today. But, It's a full arm. I do have long arms, yes. You know why? Because I'm tall. Okay. Same idea. you'll see how the algebra of this stuff plays itself out. The algebra of this works out real quick. There's not a lot of goofiness here, guys. You should be pretty, fairly pleasant with this, shall we say, for the first day or so of it. It starts to get a little bit weird when we start talking about these points inside. And that's where, like I was saying, the vocabulary can mess you up if you're not careful. Excuse me. So Rn is the angle bisector of angle LNQ, which means R lies on it, which means that RM and RP, they're both perpendicular to the sides, which means they have to be equidistant. If they're equidistant, that means they have to be equal. So algebraically, what we wind up doing here, guys, is just setting 7x equal 2x and 5, or 2x plus 25, excuse me. Oh no, what do? I am afraid of math. What's that? That would be negative 5. Right, do from the section. And again, what's your value of x? Excuse me. Now you get your value of x, always take a second and double check it, because it's super easy to do this and accidentally do something wrong. And you wind up taking 7 times 5, you get 35. 2 times 5 plus 25 is also 35. So it only takes an extra 10, 15 seconds to double check your work. When you double check your work, then you know for certain if you're doing it correctly. It's not like they tell you to do that very often in geometry. In algebra, you guys remember how I said show your work and check your answers? It was kind of, the reason we did that back then, when you're in the algebra, pre-algebra, stuff like that, they do that so that way you take the extra 30 seconds just to make sure you're doing it right. Just be a practice. So that way if you do make a mistake, you learn how to catch them quicker. That's why we do that in the lower levels of math. You don't see it very often once you get past it. Which then allows us to get to, I got one more. I know they're really tough, so good luck. Ladies and gentlemen. You get 6x and 3 is 4x plus 9. Subtract the 4x, subtract the 3, we get 2x is 6. X is 3. Okay. Everybody get that? Substitute back in to see, make sure it works. 6 times 3, oops. So 18 and 3 is 1. 12 and 3, or excuse me, 12 plus 9, I can talk, is also 21. It goes from there. One of the things that we'll be able to do eventually, probably not, I don't know if we'll get to it first semester, but definitely second semester when we get into the right triangle stuff, is that if you knew one of the angles, one of the angle measurements here, you'll be able to figure out all the other side lengths if you just know one side length. So, and we'll get to that. So let me show you what I'm talking about with this whole idea of what happens when things get weird. And I apologize, I should have blown this up for you guys, but hindsight's always 20/20. So let's see here. Okay. I'm sorry, I didn't hear you. What's that? Yeah, exactly. What I want you guys to see here, and I apologize for the drawing to be kind of off a little bit, all the dotted lines there are perpendicular bisectors. Okay? And let me blow this up a little bit better for you real quick. Take a second to try and draw this out, because there's enough information here. There's going to be enough information for us here. Oops, okay, a little crazy. There's enough information on this that we can figure out every single segment that's on there. Dotted lines, solid lines, every segment that's in this diagram, we could be able to solve for. Okay? So take a second and draw that out, and I'll explain to you guys what happens. Next time we have a big picture one like this, I'll make sure I run off a copy so you can just staple it to your notes. Probably be easier. So I apologize. Yeah, so OQ, OR, and OS are all perpendicular bisectors. Remember, it doesn't have to be perfect. It's just one of a visual-ish looking thing. That was good, thanks. How was yours? We went and saw my wife's grandpa. His birthday, he turned 90 on Thanksgiving, so we went out and had lunch with him. I haven't gone to a luncheon in a long time for Thanksgiving instead of having it at home. Weird. It's kind of nice. Didn't have to clean it. Yeah, it was really early it seems this year too. It's nice to be able to do that. Real quick, when you have perpendicular bisectors and you have big picture stuff, draw in what that does. You know that this is bisected. You know that these two are right angles. You know that this was bisected. These two are right angles. This was bisected. These two are right angles. Are you okay with that? Now, if you look closely, you'll notice that you get 3 sets of congruent triangles. Everybody see that? We've got triangle MQO, NQO are congruent to each other because of side angle side. You get NRO, PRO, and so on and so on. So you can get all these different things set up. Now, if I know that this is the point that's on the perpendicular bisector, what do I know about ON and OM? They're equal. They have to be equal. So if ON is 26.8, what's OM? 26.8. I know that O is on a perpendicular bisector, which means that if OM is 26.8, what is OP? 26.8. I know that this is a perpendicular bisector, which made two segments congruent. So if MS is 22, what's SP? RN is 26, what's RP? 26. And then lastly, QN is going to be 20. Okay? That got us all the way around the outside of the triangle, but we still have stuff that we can figure out on the inside. For example, if I'm looking at MQO, 26.8 is playing the role of the what of a right triangle? The hypotenuse, very good. The 26.8 is playing the role of the hypotenuse. The reason that it's the hypotenuse is because it's across from the right angle. Also, the hypotenuse will always be the longest segment. The reason that it's the longest segment is because it's across from the largest angle. If you have a 90-degree angle, excuse me, if you have a 90-degree angle, well, let me rephrase this. How many degrees are inside of a triangle? 180. If I have one of them is 90 degrees, how many degrees are left for all the other two angles? Only 90. So no matter what, you'll never get another angle bigger than 90. So that's why it's always along the side. Now, what was that whole thing about, side lengths of right triangles and figuring out missing sides? Something that we've used, but we haven't really definitely defined yet. Something you've all seen about right triangle. Yep. Which means we're solving for one of the missing side lengths using Pythagorean theorem. So we know it's 20 squared plus something squared is 26.8 squared. You okay with that? Yes, ma'am. This is what I did here, MOQ? Yes. Now, you guys all agree that you can just press buttons to figure out what 20 squared and all that is? Now, if I do this, I can say that B squared is going to equal 26.8 squared subtract 20 squared. Now, what I want to do is make sure you guys know how to use your calculators. So, in your calculator, it doesn't matter which one you have, you all have the same functionality. What I want you guys to get used to is how do you use what's called the answer button. The answer button is on the bottom right by the negative. It says ANS, where you have your button that says second answer to get it to open. Everybody see that?
Yeah.
So here's what you do in order to use it. I don't know if you have that one on there. Is there an ANS button on the bottom right also? Okay, I'll have to help you with that one. There's bottom right, it's the same spot. What I would do is type this in, 26.8 squared, subtract 20 squared, and hit enter. Okay. When you do that, you'll have something on your screen that says 318.24. Everybody got that? Don't press any other buttons yet. But right now, that equals b squared. How do you undo squaring? You square root it. So here's what you do now. Don't press anything else but this. Hit your second square root button of your answer and hit enter. By using the answer button, you don't have to retype in stuff. Okay? You don't have to retype in your 318.24. What it's doing is that it's keeping, the last time you hit enter, that creates whatever the answer was. I swear to God. Yes, now yours is that you hit enter first, then hit second. Oh, sorry, you don't have to. Hit square root of your answer. Just a little bit because you have a straight square root button. Yes, ma'am. Sure. Again, what you do is you type in 26.8 squared, subtract 20 squared, hit enter. Now you have that, right? Now hit second. You know where the square root button is? Can you find it? It's on. When you hit second, you found it. Now hit second again and answer. It's the negative button in the bottom right. So it should say A and F's on it. Answer is like in the little green. And now hit enter. I always round to 2 decimal places, so if it's 17.839, what would you write it as? 1784. Okay. So what I'm saying here, guys, is that we'll be able to figure out all these extra little pieces thrown in there. Same thing here. If I wanted to figure out what this segment was, I'd take 26.8 squared, subtract 22 squared, and it'll take the square root, it gives me this. I do it again for here. Right? It's little tricks like that that we'll see throughout the course of these bigger picture problems. Right? Let me give you a handful of these to start out with. We'll work on those, please. Correct.